Hello, everybody, and welcome to Chapter 14 in Dynamics. This is Professor Algara with our lecture video now covering an important chapter of the book which talks about work and energy and interactions from the dynamics standpoint. So, a force does work on a particle when the particle undergoes a displacement along a line of action of the force. Okay, so basically, when you have a path, a curvature or straight path or something like that that comes from S1 to S2, then if this particle goes from that point to the second point due to a force, then that force is causing work on the particle. Okay, work is defined as the product of the force and displacement, both of them components acting on the same direction. So if the angle between the force and displacement work is theta, the increment of work du, done by the force will be given by this equation. And then by using the definition of the dot product and integrating the total amount of work can be written as the following formula. And this is kind of, what it shows as far as the diagram. But as always, I always like to kind of explain you with my own words what that is, and I want you to remember what we call from statics when we were studying the dot product of two vectors, because that's the base knowledge you need in order to understand what's happening here. All right, so let's put this in words that we can all understand from the previous definition that we had on the book, and that's what you'll read. So pay attention to me right now. So we have our path, and let's call this point 1 and then point 2, and our particle will move from 1 to 2, and this particle it's moved thanks to a force that is acting on the particle, that is making this particle to move. And this particle goes a displacement, from 1 to 2. And we're going to call that in terms of differential as dr. And dr is a vector. Don't forget, we're talking about vectors here. If I want to expand this a little more, the angle between them, we're going to call that theta. And then, a little more from the origin to here, we have our, you know, displacement, and then our location, sorry, location vector, and then r prime. All right. And that's basically a little bit of the representation of what we have, in this picture right here. So what do we do with this? We have to take the definition of work. As you know, it's force times displacement when we're talking about, or the dot product between these two vectors, the force and the displacement. If you have those two together and you perform the dot product, then you will get your work done, on a particle. What is important here to remember is that equation from the dot product that we had in statics. If you have the dot product of two vectors will be equals to the magnitude of each one of those vectors, the multiplication of them both, and then that multiplies the cosine of theta, and that will give you the dot product as a value that you're looking for. Okay, so if you have, A dot B, that is equals to the magnitude of AB that multiplies the cosine of theta, being theta the angle between both of them. If I write this with this information that I have on the diagram that I'm showing you, it'll be something like this. So in terms of differential, the differential of work will be equals to the dot product of the force times dr. And just remember that the magnitude of dr as a vector is called differential of displacement, and we're going to call this as ds. That's the magnitude. So if I use this and I plug this into the equation to perform the dot product, I will get something as it is on the book as this. It is f times ds that is been multiplied by the cosine of theta. And that's the definition of work. When you have that, right, all you have to do is integrate on both sides, in order to get your work performed from 1 to 2. And that will work from any point in time to a second point in time, okay? Going from this point to that point. Remember that the units for this Okay. In the SI system will be equals to joules or newtons per meters, and then IPS or the English system will be equals to feet times pounds. Okay. So everybody, just I hope that you're understanding this because this is a little bit of an explanation of this whole blah blah blah. What we need to remember from this, and I'm just using definitions from statics. Work is defined as force times displacement. The dot product when we're talking about vectors, since we're talking about vectors, then we're going to perform the dot product by using the displacement and the force and then the angle between both of them. Okay. So following a little bit more. So f is a function of position, which is usually what it is, right? This becomes, like I show you, an integral that can be defined as this. You know, f and the angle are constant, so we can take these two out of the integral, and then we will get a more simplified equation, which is this one that we have right here. Work is positive if the force and the movement are in the same direction, all right? Remember that. If the force is causing the particle to move into the same direction, then your work will be positive. But if then, if the opposite thing happens, they're opposite, um, they're opposed, sorry, then the work will be negative. If the force and the displacement directions are perpendicular, then the work is zero, okay? Due to the cosine of 90 degrees. If that force and the displacement, if they both have only 90 degrees, then your work will be zero. And remember that because whenever we have normal forces or forces going into the y direction that are forming 90 degrees with the displacement, then there's no work over there, okay? And we're going to start defining a little bit of the work done in different cases, weight, sprints, and things like that. So let's go with the weight first. So the work done by the gravitational force acting on the particle can be calculated by using the equation, force times displacement. I'm using the same thing as I defined at the beginning. Okay, force times displacement. But in this case, your force will be the weight, and the weight is always pointing downwards, and that's why that work will be negative. And then dy as the change in height of the particle, right? You had S1 right here and S2, and as they change in height, then you will have a work done by the weight. Okay, simple as that, very straightforward, and nothing to be complicated about this. This one is a little harder, okay? Work of a spring force. When stretched, a linear elastic spring develops a force of magnitude equals to, force of the spring, it's equals to the k of the springs times the displacement, okay? Being the displacement, initial position and final position are involved. As you know, the k is the spring stiffness and s is the displacement from on a stretched position. The work done the work done of a spring the work done of a spring force moving from the position S1 to position S2 is defined as this. And this is very important because people get confused. So one thing is the force of the spring and another thing is the work of the force. Okay? Work of the force is defined as force times displacement. But you already have displacement involved in the equation of the force of the spring. So therefore, when you're performing your integral, you will have the force of the spring, which is this one right here, and then you will have ds. When you perform the integration, you will get the following equation, which is 1/2 of k final position to the square, and this is quite important, minus the same equation, but with the first or the initial position to the square. Okay? If the particle is attached to the spring, the force, you know, on the particle is opposite to that exerted spring. So therefore the work performed by this will be negative. So just look at it this way. If you are, for example, trying to stretch this spring, right, in that direction, to the particle, the spring is trying to push it back. Okay? And when that happens, the work performed on the particle will be negative. Or if you want to see it that way, if the spring is helping the particle to move along S, then that work will be positive because it's helping. But if the work is preventing, the particle from moving, then that work will be negative. Basically, if you take a look at this, it's the same definition that we had at the beginning. Just apply to spring. If it's helping the movement, then it's positive. If not, then it's negative. And I put together these little, remarks because this is quite important. And obviously, when I perform exercises, you will see it a little better. But it's very important that we summarize everything learned until now. So the equations above are for linear springs or only. And just remember that the force of the spring is Ks. Okay? K is the constant of the stiffness constant of the spring, and then S is a displacement. The work of a spring is not just spring force times distance, okay? People fall into this trap very often. They forget about the second displacement because they get confused between force of the spring, and work done due to this force, okay? You use this force, you plug it into the work done by the spring, and then that's how you get the square. People forget the square. And more importantly, always double check the sign of the spring work. Like I told you as an example, right? And you will see that when we have exercises, but if your spring is helping your particle to move, then the work done will be positive. If not, it's negative. Okay, one of my favorite topics, principle of work and energy. Guys, just save that, put a pin on it because you will utilize this when you get in thermodynamics. It's the exact same principle. So by integrating the equation of motion, which is this, sum of forces equals to mass and acceleration, we can get the principle of work, okay, or how work and energy are related, okay. So let's just read through it. So by integrating the equation of motion, sum of forces equals to mass and acceleration, just recalling that the only acceleration involved would be the tangential acceleration, and you will tell me why is that. The principle of work and energy can be written as the sum of forces of all the energy it's equals to kinetic energy, where delta or the sum of U is the work done by all the forces acting on the particle as it moves from point 1 to point 2. Work can be either positive or negative. When it comes to T1 and T2, those are kinetic energies of the particles at the final and initial position respectively. So therefore, your T1 will be equals to 1/2 of the mass B to the square, and T2 will be equals to 1/2 of the mass B2 to the square. Kinetic energy is always positive, since it's a scalar. It's a scalar value. Okay, so I'm pretty sure we covered something like this in statics. But just remember, kinetic energy, just as definition, is 1/2 of the mass times the velocity to the square. Why is this important? Okay, so if you have, and I love to do this because I feel like I'm helping you, that's S, and you have your point 1 and your point 2, right? It's going from 1 to 2. And then we have the particle that is traveling. This particle will have a tangential force or velocity, and we also have something that is called normal, right? So this is all the forces acting on the tangential, and then this is all the forces acting in the normal. And remember, I told you, okay, no, I don't wanna get more complicated. The sum of these two will give me the resultant forces, both tangential and normal. What is important about this, it's why are we using just the equation as the sum of forces of tangential? It's equals to mass and tangential acceleration. The normal acceleration will make 90 degrees with the displacement, and therefore that component is zero. So that's why we're not focusing on the normal component of these forces, okay? They will make with your displacement a 90-degree angle, and therefore, as we defined at the beginning, that will not have any interaction with work, and that's why we don't worry about that, okay? And just recall that your tangential acceleration is equals to the speed, that multiplies the change of this respect to the s. If I plug this into this equation, I will get, and this guy right here is the resultant forces. All the resultant forces are equals to mass v dv ds. If I rearrange this a little more, I will get, resultant forces ds that multiplies mass v dv. Okay? So far, if I integrate this on both sides, this one from S1 to S2, okay, and the other one from B1 to B2, I have to know that these things are all the work done by all forces. And this one right here, it's just all the kinetic energy involved in the whole thing. Okay, so if I rewrite this, I will get that this is all the work done from 1 to 2, and this is equals to 1/2, by performing the integration of this guy, 1/2 of the mass that multiplies b at the end to the square minus 1/2 of the mass, which multiplies v1 to the square. Okay, and that thing right here is what is called on the book kinetic energy at the end, and this one right here is kinetic energy at the beginning. Okay, and why is this important? Because when I rearrange this equation, I will get something in the book that is called as this: T1 plus all the work done from 1 to 2, it's equals to T2. How can we make sense of this formula? It's very easy, guys. At the initial state, you have all of the work done by all of the forces, right, involved, and that could be spring forces, things like that, but all of the work done. And then you have the kinetic energy that all these phenomenon is it's doing, into your system. So when you zoom all of those kinetic energy plus the work, that's what will tell you exactly what you have at the end. And I don't want to get into thermodynamics or anything like that, but this is how energy will be um, related in these two interactions between kinetic energy and work. Okay, so the kinetic energy at the beginning plus all the work will be equals to all the energy that you have at the end. And if you just take that and you try to comprehend what this tells you, then you will be able to perform any exercise. But when I'm telling you any exercise is literally any exercise, because that's what we need to understand. We have two stages, one or beginning and end, right? So whatever I have at the end will be the result of all that work performed by those forces and the kinetic energy that is performed from moving my particle from 1 to 2. All right? So this is just going through as a whole definition. Note that the principle of work and energy, it's this one right here, is not a vector equation. Okay, this is a scalar value. You will get a number. Both kinetic energy and work have the same units. That's why you can just, use oranges and oranges and not apple and oranges. So for the SI system, as I told you, that's the units for this equation when we're talking about energy. And for the English system will be this. The principle of work and energy cannot be used to determine forces directed normal to the path, as I told you, because they will form 90 degrees and therefore that will make your work zero. They do not, those forces do not, they don't do work. Okay? The principle of work and energy can also be applied to a system of particles by summing all of the kinetic energy of all particles in the system and the work due to all forces acting on the system. Okay, this is just more of the definition that is given. And finally, there is a special case that the book has, and I wanted to include it into the presentation because I'm pretty sure people will get confused by this. But I'm just going to give you a summary and just look at, before we read through the theory, let's just look at these two pictures that we have. You have a box that is sliding, through a surface from point 1 to point 2, okay? And they go on displacement thanks to the force acting to the right, okay? What is happening here when we do a free body diagram is that now we're including, the force of friction, that is causing because we are considering friction. Okay, this is not an ideal case where friction is not considered. So we're considering friction. When we are writing the equation between work and energy right here, what is happening is that we are including the work done due to this force, which is work, it's equals to force times displacement, and that's what you have right here. And it will be positive because it's helping the displacement, it's moving with the direction. And then opposite to that, you have the frictional force, which is equals to mu k times the normal. And that has to be multiplied by the displacement in order to be work, in order to be energy. Okay, so that's what the formula would be rewritten as. So you have the kinetic energy at the beginning plus, right, because it's helping the movement, the work done by the force P times the displacement minus, because it's opposite to the movement, mu k times the normal, which is the frictional force, and that has to be multiplied by the displacement. And all of that is equals to your kinetic energy at the end. And just for you to know, we're not considering heat, right? And that's something else, all right? That's obviously the friction generates heat, and to be realistic, that has to be considered for us to do this equation, but it's not included as of right now because of the level that you have, okay, as mechanical and civil engineers. So let's just read through this so we can, make sense of ourselves. The case of a body sliding over a rough surfaces merits special consideration. Consider a block which is moving over a rough surface. If the applied force P just balance the resultant frictional force, a constant velocity will be maintained. Okay, the principle of work and energy is applied with the equation, and I just explained to you with the pictures what this is. You know, we know from experience that friction generates heat, a form of energy that does not seem to be accounted for this equation. Okay, but as you move into your engineering career, you will know and you will learn that we actually use all of the different interactions when we are studying systems such as this one. The key or the takeaway with this is that you always need your free body diagram on your particle so you can see all of the different forces acting to it. And if you use those forces which are causing work into this theory, then you will be able to rewrite the equation as you need it, okay, or as needed, depends on the case. All right. And with that, we conclude just for this video what we are covering. This is just a small taste of chapter 14 since we have a first examination in this week. I don't want to get, you know, a lot more into that. We're going to open the next video with exercises, so you can see the application of all these theory. All right, that's it for this video. Let me know if you have any questions, and if you don't, I will see you in the next one. Thank you.